Okay.
Okay.
Because that time there was a
so I just saw a message saying that it's live stream now.
Okay.
Okay. So then let us start. Sorry, folks, for the delay in starting. So let me start by first of all introducing our guest today, Dr. Jayagunda Perumal. He is a professor in the Wadia Institute. First of all, introducing our guest today. Sorry. Is there, I'm getting a feedback. First of all, introducing our guest today. Sorry. Hey. Hello. Silde, I'm getting a feedback. Why is that? Yes, today. Sorry. Hey. Hello. Silde, I'm getting a feedback. Why is that? Yes, today. Sorry. Hey. Oops, sorry. Again, there's a glitch. Why is that? Is it because of my problem? What? Hello? Okay. Maybe this problem is not there. I don't know. Or at least I can get it. So, Professor Perumal is a member of the Wadia Institute of Himalayan Geology at Dehradun, and he heads the structure and tectonic group. Yeah, can you people hear me? Sorry.
Yes, you're audible.
Okay, fine. Okay, so he's the head of the the structure and tectonic group. Apart from taking care of some other maybe administrative matters, he's also the associate editor of the Himalayan Geology Journal. He is one of the key scientists in initiating research in earthquake geology in the Himalayan region. His studies have been useful in the prediction of earthquakes through developing an understanding of the relationship between the buildup of strain and its release in the form of earthquakes. This is also useful in understanding how mountains form and to understand and to estimate the seismic hazard in the planet's largest continental thrust system. You all know that the highest mountains rise because of these two plates. One of the plates, the Indian plate, is going underneath the Asian plate. That's why we get the high mountains like the Everest. Some of the many honors that Dr. Perumal has received are the Annie Talwani Memorial Prize for 2020 by the Indian Geophysical Union, the National Geosciences Award 2018 by the Ministry of Mines, and the SS Made Award in 2016 by the Geological Society of India. He has one patent and is guided, of course, several PhD and MSc and MTech students. So I look forward to an interesting colloquium by Professor Perumal. So the floor is all yours, Professor Perumal.
Thank you, Professor Vivek, and good evening to all of the participants. So what I'm going to do for another, I do not know what is allotted time for me. Professor Vivek, I think it's about 1 hour or 45 minutes.
Yeah, maybe about 55 minutes.
Yeah, that's true. So
and
I
then
will
there'll be questions, I hope. Of course, there might be questions in between also.
Yeah, I'm glad to take up those kind of questions. You can pass me at any point of time because we are on the online. So I should not feel that I'm just talking in front of my laptop.
Sure.
So basically what I'm going to talk today for another 45 minutes, Himalaya, that's a lofty mountain in the Indian subcontinent, of course, in the globe, and how the Himalaya forms and how the earthquakes develops. So that's the title. Basically, in this talk, you will understand how the mountain building develops basically and builds up the energy, all these things. So it will be more of like a layman kind of thing. Any discipline people, they can understand what is being taught or what is being taught today. So that's the scope. Okay. Basically, you can see on the screen. I think I'm audible to everyone. I wanted to listen from the participants.
Yes, you're audible. Perfectly audible.
Okay. So
only your camera is off, sir. Camera.
Yeah, your camera is off. That's right.
Okay. You want?
It would be nice if you have the bandwidth. Please put on your camera.
I think I put the video on. Now it's see.
No, we cannot see.
Your face is not visible.
Okay. I do not know. Something went wrong because even I don't see my face.
But you are not visible. It is blank actually.
So is it so? I was also trying. I don't know, something setting.
But Perumal, if it is okay.
Yeah, maybe I will solve later on actually.
Anyhow. Yeah, I think you please go ahead with the talk.
Yeah. So basically on the screen, you can see that's a Kathmandu Darbar Square. And this building got collapsed in 2015 Gorkha, Nepal earthquakes. Mm-hmm. See, in Himalayas, the earthquake is a ritual phenomena, basically. In fact, the microseismicity, what we do, the seismologists, they monitor the Himalayan earthquakes. And we do record, say, 10,000 to 20,000 numbers of earthquake, micro earthquakes, we say less than 2 or 3 magnitudes. So the interesting question is that in Himalaya is that, so when will be the big earthquake? There will be a future disaster. That's very important because construction and destruction and reconstruction, that's, I said, it's very ritual. So the obvious question is that, because as a scientist, we always ask why, when, and what. So this is very important questions. How to do that? See, in a basic science or a natural science, this is a geological subject, is a natural science. In applied science, we know that 2 plus 2 is 4. Even if you wanted to prove empirically, there are possibilities out there. But in a natural science, it has a lot of variabilities. That's what you are going to understand, what are the complex problem. But still, we can't wait since it is a very complexities involved. But we have to understand. Because my perception after having done of 20-25 years of my research in Himalaya, the nature has a unique pattern actually. That is what I'm going to show you basically. But if you go further, deeper and deeper, probably the predicting of earthquake is also possible. This is what my understanding is so far. But I'm not saying that it can be done within a very shorter time, but it can be done through different perspectives. So that is about this talk basically. So my screen, okay. Where I'm working basically, it's a Wadia Institute of Himalayan Geology. It comes under the Department of Science and Technology. We just developed the geoscience, and also we wanted to linkages with many universities and research institutions. That's our mandate. And also we publish a lot of papers on earth science related issues. And we wanted to understand the Himalayan geology better and better. And also we have the dedicated program for PhD students. And now recently we have tied up with the ACSAR. Previously, we don't have any deemed university status, and we used to get the PhD done from other universities. But now we have a full-fledged ACSAR, that Academic Scientific Innovative Research. We have a MOU with them so that student can directly supervise for the concerned scientists in Wadia Institute. This is the campus you can see. Okay, so the talk of my today's talk, what I'm going to do is that we will talk about the evolution of Himalaya, how Himalaya is evolved. Then active faults, basically the earthquake produced the active faults. So we will be talking on that aspects. Then how we can quantify this basically, because any scientist, they wanted to know the science in numbers, in the fact, how much energy is getting accumulated and how much is being released. That is what the science is looking for now. So that part we will be covering, how it is getting quantified. Then what is the implication of this research? What is the use of this kind of research? How does it going to matter for any kind of a planner or administrator? Because after all, we have to do the science on a SWOT basis, because every science has to be sellable to the market. So that's the important. You can see that's a beautiful map. In fact, somebody has sent me this. Professor Vasan from Australia University shared this image. In fact, it's a very beautiful image. You can see, let me take the pointer. You can see there is a drastic elevational difference between the Indo-Gangetic alluvial plain, is where the foothills of the Himalaya, where the mountain and plain area meets. That's a place called the foothills of the Himalayas. And of course, we have the Kappa region and Vindhyan and Aravalli mountain systems are there. They are all old-aged mountain systems. But whereas if you look at this, there is a drastic elevational differences. And also this Himalaya is a lifeline for not only for the Indian people, for the adjoining region also, because these high peak mountains controls many dynamics that you will understand once the talk progresses. If you see very close up, this is what the orthometric elevational difference. What I'm saying is that there is a sea level elevation and there is a orthometric, means there's a relative increase in the elevation. That's why it is very active, because this orogeny is 6 millimeter per year. It is growing vertically, and due to the horizontal force, it is moving at the rate of 20 millimeter per year towards the north. So that's why we have the enormous height is being built up. Now, how this mountain really formed, basically. Now, before the 100 million years ago, there was a Indian subcontinent and one sea, basically. But if I go back in a much earliest period, we have a one ocean and one land, like Pangaea and Panthesia. But I'm not going into that detail, but somehow due to the drifting mechanism, or basically it all happened due to the plate tectonics. So that leads to the breaking of the major subcontinent or major continental plates. So basically in sometime in 132 or 125 million years ago, this India broke off from the Antarctica and Gondwana regions because of the rifting and other thing. Then it started moving, basically. It started moving towards the north. So that is what you are seeing there. This is the little Indian subcontinent. We have the mantle and this is the crust, basically. If you think about the crust, and we have the continental crust, we have the oceanic crust. So those are very fundamental aspects you can see in many of the textbooks. But this crust thickness are variations between the continental and oceanic crust. So what is happening is that because of this Indian northern margin is attached with this Neotethys, and it got undercrusted, basically. It's a subducted, basically, due to the plate tectonic concept. The sea got vanished. This is the story due to the plate tectonics. So you can see that from 30 degrees south latitude all the way to it is 35-degree north latitude. So this is how this Indian subcontinent is traveled. Basically, the convectional current, because hot magma is there, it is keep on giving the energy to move these plates, and that's how we know that mid-Atlantic ridge and mid-oceanic ridges, these are all giving the spreading center. It gives the mechanism. Then I will come to the point a little later, and you can see that what is the rate at which it was moving. Basically, the rate was very, very high sometime in 80 to 50 million years ago. You can see this is the velocity motions they have inferred from the various scientists, and slowly now it has come to the, say, 20 millimeter per year, basically. So in a different cross section, you can see that, closer look that this Neotethys is how they are totally closed. You can see in a layman language that's called archipelago. Basically, if you go to the modern, maybe, whether do I have the slides? I must be having somebody here. Okay. Yeah, you can see that this is the east coast. We have the Andaman Sea, and this is the port player. This is Java Sumatra Trench. You just imagine that this was the scenario was held sometime in before the collision zones. So that was the same scenario. Then the sea got really disappeared. Now just you can imagine that how much energy was there and how much. It's not happened in a single day. It took geological time scales, and totally this Neotethys disappeared, and whatever the sea was there, that we can see on the future zone where the Ladakh region is located. It's called the ophiolitic melange. That's what we say. So it was an archipelagic origin. It's a classical example because it was having the sea on either side of the land, and slowly the sea got disappeared, and this Indian continent is undercrusting now. Previously, it was a subduction because of the heterogeneity in the oceanic lithosphere. There is a density variations. Larger the density, the material goes down. But now the continent is of a same density, but still because of this archipelago effect, this continental crust is under thrusting, because sometimes we say subduction. Subduction is usually referred to the where the oceanic crust is subducted under the continental crust. But if you look at the cartoon here, it is the Indian subcontinent and the Eurasian plate, both are of same density. That's why we are saying under thrusting. So basically, it was a mountain orogeny developed because of the collisional tectonics. So whatever we see reconstructed based on the geological observation, which we have seen all along the lay regions, you can see on that map very nicely. This is called Indo-Songpo future zone. Basically, you can see very well evidences for the oceanic sediments has been piled up, which has come onto the surfaces. This is what you can see very beautifully on that particular region called north of the Ladakh. This is the Indo-Songpo future zone. These are all some of the batholith you can see all along these Himalayas. This is a general Himalayan map. All these cross sections, everything is involved with the different researches. So basically, now this is the scenario. We can see that. I think this is bothering me anyhow. Okay, so this is the ocean landmass. This is the Asian plate, and this is what the whole of this bunch of this mountain system is the, you can say, accretionary wedge or a fold thrust belt. This is what in geologically it has been said. And you can see these mountains, basically, as I said, in the Indo-Gangetic alluvial plain or Indo-Brahmaputra alluvial plain, there is a plain region, and slowly the elevation increases. So we have the Shivalik or sub-Himalayan range. If anybody is familiar with the Mohand or Biharigarh, these are all the regions. You can see the sudden elevational differences. Then it goes to the lesser Himalaya where the Mussoorie Hill is located, or Darjeeling or Sikkim Himalaya. Then we will slowly go to all these four dams, that is Gangotri, Yamunotri, Badrinath and Kedarnath. They are all sitting somewhere in the higher Himalayas. That is called Himadri. And this is, of course, the trans-Himalayan part. It is basically Ladakh and Leh regions. In the north of that, we have the Tibetan region. This is what the general cross-section. And now, basically, how do we know that Indian plate is moving, basically? So we have the velocity vectors, and we continuously monitor the GPS global positioning satellite. We install it at Bangalore in various places. And with reference to the velocity frame, because now India is fixed, now this is moving towards the south. When it is Tibet is fixed, then it will move towards the south. So that's a different kind of relative motions we try to infer that. Now, if you look at the Himalayan mountain belt, the earthquake is very common, as I said at the beginning. We have the microseismicity occurring all along this, basically the foothills of the higher Himalaya. I will come to that a little later. Now, why these Indian plates are moving and why do we have a micro earthquake or earthquakes in Himalaya? Basically, you can see there are many spreading centers, basically. You know that ocean grows, land gets recycled or land gets exhausted due to the subductional processes. So because of the sea is getting growing, and because of this spreading center or a spreading rate, that decides the movement of the Indian plate. Not only Indian plate, there are many plates it moves with related to one another. For example, if you see the East Pacific rise, it is also moving, and that leads to the Northern America and Southern America and part of the Aleutian countries, they get the earthquakes. In mid-Atlantic regions. So now the question is that where come this northern margin is getting deforming? Means it is getting like a higher Himalayan or a lesser Himalayan kind of a scenario. So that is very important, because we declare this is, as I said, on the eastern margin and the western margin, they are not deforming, they are passive margin. But whereas in the northern part, it is an active margin. So we do not know, someone might ask, so why this basically this part of this particular continent, say this continent is not having any kind of a deformation or active deformation. So that is a main research, how they are really converting. Because if you look at the Indian subcontinent in subsequent slides, this is what the scenario that. Basically, we have a Carlsberg ridge and we have a central Indian ridge. So collection of this ridge pull, basically, or a push, that leads to the 3.5 centimeter per year this Indian is moving, basically. So now one can argue, so when Indian plate is moving at a rate of this much centimeter per year, then how come this western passive margin or eastern passive margin, they remain ideal? That's a big interesting question one has to really understand. When this passive margin become active margin itself, and a separate research is required for that, but nevertheless we have the northern margin, it is active because we have the Himalaya is witness. So basically, because of the ocean growth, our ocean is getting spreading at the rate of, say, the collection of all the spreading, it would be around 10 millimeter per year. So that leads to the movement of the Indian plates. So that we can see not only from the geodetic or the GPS instrument, we also see from the ocean records how these magnetic anomalies are getting changes. There are many scientists, they do such kind of inferences. So that all says that Indian plate is moving. This is what I was talking to you. There's a modern analogy that basically we have the Andaman Nicobar Island, we have the barren volcanic islands, and we have, this is the Indo-Brahmaputra range, and this is the Java Sumatra trench where the Christmas 2004 earthquake happened actually. So now this is the scenario. Just imagine that you close this sea basically, then you allow this margin to interact with this Java Sumatra trench. Then you might get this kind of a scenario, like a series of mountain will form along the eastern passive margin, so not become an active margin. That's a kind of an modern analogy I can give you so that it will be easy to understand for you. Now, because of these movements, basically due to the convergence of the Indian plate under the Eurasian plate, then there should be a consequences. What is the consequences? So we should have the tectonic, basically tectonic and climate. What we say that the processes which is operational under the Earth's surfaces, it's called endogenous. So those kind of processes totally controlled, basically that's called the tectonic component. And exogenous means once the landform is being built, basically due to the earthquake, it got uplifted, then the surface processes take care of that. So when these two guys, they interact each other, then that leads to the natural hazards, basically. So they are just, you can't really decouple both processes. It is just like a nail and finger. It's like a wife and husband. You can't really say that he has done more and he has done less. Nothing is comparable, basically. But of course, the decoupling of these two processes is very tedious, basically. Why tedious? Because it's very complex to decouple each of these components. That's a very important aspect. Probably many of you might have watched the movie called The Core. Basically, some group of people, they want to control the magnetic effect, gravity effect in the form of putting a big project, drilling the core of the earth of the core, that leads to, they can control the whole of this magnetic and this kind of field. This is a kind of a movie, you should watch that movie, I think. The movie name is The Core. Then you will understand how this whole earth is being controlled, basically, by this kind of natural processes. So now, I will be talking only on the active fault. That's a tectonic processes, how that is kind of an earthquake forms, what would be the causes, and how basically earthquake forms. That we know that because of the motion of the Indian plates. Now, if it is moving, then why the earthquakes are confined only along the Himalayas? As I said that this is an active margin. We don't have any kind of passive margin related earthquake, but we do have some kind of a passive margin related earthquakes due to the flexural effect of the continental shelf breaking. So that's very minor. And also we have the earthquake within the Indian subcontinent, but their repeating time or recurrence is very larger. Even if it comes, it will be 6 magnitude, not even more than 7. We have the Jabalpur earthquakes. Sometimes we have a Latur earthquakes. But they're all different setup. There's an intraplate setup with that. So, but when you compare to the Himalaya, the earthquake recurrence interval is something higher in the Himalayan regions. So that's why the Himalaya is attractive for many of the people to do research on earthquake geology. Okay. Now, as I said, that fault is different. Fault means something is weak, basically. Many people try to study the fault in a different perspective. As I'm an earthquake geologist or a paleoseismologist, I am very much interested to see the topographic and landscape where people can be settled, where the topography is nice. So I'm very much interested to study on that. Then I'm also interested that how this deformation create in lithosphere in response to the plate tectonics, because in turn it's generate the earthquakes. So I'm very much interested on that. And overall, it affects the seismic hazards. Some people are very much interested for hydrogeology, control the permeability, they study on that. Some people wanted to exploit the oil field and wars, they study on economic resources. So most of the fault, even if you see the aquifer or where you get the groundwater potential, shear zone, faults are very much controlled in the form of development of groundwater and aquifer management. So basically the objective of the geoscientists vary with subdisciplines. That's the key point from the slides. So there are different types of fault. But essentially what this fault is basically the stress direction, that the sigma 1, sigma 2 and sigma 3 switch basically. That is the main concept in this. But in fact, as I said earlier, that in a natural science, you can't clear cut this is what it is happening, because we have the combination of this normal and reverse also, and also with normal with strike slip fault and reverse with strike slip fault. So there is nothing is clear cut that it will have only normal fault. By and large, in an overall picture, we can very well classify that is an extensional regime that is called normal fault. That can be seen on that is basically on the Utah Valley, or especially in the Western United States along the salt range. There you can see the extensional regime. And reverse fault you can see in the Himalayas and many places in San Andreas fault. And again, transform and strike slip fault, again you get the Istanbul in Turkey, we have the North Anatolian fault, and we have in Western United States, there are many strike slip fault, that is the San Andreas faults. So these are the major type basically, but when you go to the field, you can see the combination of both. But when you talk about the different fault zone,
Can I ask a question at this time?
Yes, please.
I'm not really sure what you mean by the normal, reverse, and transform fault types. Could you please explain a little bit in terms of geometry of what is going on in the faults?
Yeah, that is what I'm going to do. The next slide is like that only.
Okay.
You will understand better than my conversations. Okay. So now if you look at the fault, how basically one can visualize that fault basically, that you can see that there's a plane in which there is a movement take place. There are joint, there are fracture, and there are fault. So is there any movement with respect to the weak plane if they are moving one another? So basically relative, but when they are moving with respect to that particular fault plane, then we call it as the hanging wall and foot wall. So this is what it is clearly mentioning, that when head is pointing towards when you stand along the fault plane, then the head portion will be the hanging wall and the down part will be the foot wall. You can see that this is the block diagram. You can see the triangle, and this moves, the top part is the hanging wall. Now you can see how this, and not only head and tail, it is basically the age matter. Age means the older rocks in a thrust fault will be coming from the deeper level. That means when you have the thrust fault, that means you are adding the thickness of the crustal region more. That is called, you are adding the more and more material on the hanging wall part. In a case of a normal fault, when it comes to the normal fault, I will talk about that part. Now you can see some slide is missing. Okay, anyhow, let me see that. Okay, now this fault, this is what the reverse fault is there. You can see that this brown component, that means it has been doubled basically. So there basically the horizontal sigma 1 is then a horizontal direction with respect to the weak plane. So this is what the thrust fault is. Now if you go back to the normal fault, this is the normal fault. Here you can see that there's a rifting because the crustal extension is taking place. That means horizontal stress is going away from that. That leads to the thinning of the crust. So that leads to there will be a crustal thinning, and that leads to the downward motion. In both fault, there is a dip slip component. The meaning is that the relief can be generated. That is the important aspects. You can see on the field, the normal fault in the Dixie Valley, you can see this is the range front. You can see there is a blade-like a structure. Basically, the mountain front has gone down this side, hanging wall gone down this side, and footwall is gone up. That means in a slip component like crust fault and normal fault, the orogeny or a mountain building process will have the elevational gaining will be there, regardless of they are whether normal fault or a reverse fault. So basically, this is the 1954 Dixie Valley Nevada earthquake that has preserved that, how this earthquake really contributing in development of the mountain orogeny started thinking in that process in 1950 only. Now you can see on other view how this mountain front is getting deformed. There you can see this is small baby mountain is developed on this, and this means this is gone down, this is growing up. And again, this is a closer view how very beautifully preserved this, because it's a very arid topography, arid climate, so there is not much monsoon. Still, this landform is very nicely preserved. And one more thing is very important is that now, basically, what is this fault? The fault in which most of the static stress is getting released. So that means that geometry and their orientation will be uniform all along the strike of this particular fault. See, when the dynamic stress, that is a different aspect. Dynamic stress, when it releases, it will have several uncertainty or several governing factor, maybe hydrology, shallow water table, those things. With respect to that shallow or dynamic stress will be reciprocating. But whereas in a static stress release, where this kind of fault is seen, especially on the foothills of the Himalayas or any kind of the foothills of the range where the mountains are active, you can see the static stress is released in the form of an earthquake. That will be, you can see those landforms very nicely, which is almost similar in geometry and characteristics. That is very important. So this is what the strike of the fault, because this place here, this part is moved up, this part is come down. So that means there is an elevational differences. Now you can see on a different side, this is a Fairview earthquake surface ruptures. When Fairview earthquake took place, that time this mountain has been disrupted like this. Now there is another aspect in the same region where we have the normal fault with the strike slip fault. Basically, this is a ridge. This ridge should have continued on a same way, but ridge has been offset with the strike slip fault. This is what the important. Now, this is a reverse fault, I have already mentioned it. Now, this is a typical example where the Chi earthquake in Taiwan, the school ground has been broken and that leads to the earthquake fault scar on the Chi. This is the footwall and hanging wall. And even in the Chi, they have preserved a live museum on Chi earthquake, and one can visit that how this earthquake can really damage the ground surfaces with a lot of information on that museums. And this is what the Kashmir earthquake, that is in 2005, Muzaffarabad earthquake, that damaged this whole of this Neelam Valley. You can see there are different terraces, basically terraces or the formation due to the river flowing in a different dynamics that leads to a different level of terraces, because these terraces form due to the tectonics also. As I told you, the terraces can also be formed due to the extreme event also because of the agglutational point of terraces. But in the case of an earthquake generated terraces, that can also be from the tectonic processes. So you can see that these terraces on the base of the terraces, whole landform got disrupted during these Kashmir earthquakes. Now, another classical example, this Kashmir earthquake produced the folding also. Basically, there's whole surface has been totally warped, basically, just like an, what you say that there's a bread roll, you can see that. Such kind of rolling effect has been done that has devastated totally. Almost 10,000 people have been died on this. So there's another example, classical example in the foothills of the Nainital region where we have the normal fault. There's a beautiful fault scar. And one more thing I wanted to show you, or I wanted to clarify you, whenever the component of the particular fault is steeper, the fault scarp is very, very short. For example, in the case of an crust fault, it is not very clear because the dip of the particular fault must be very shallow. When you bring the deep component to the surfaces, that leads to the curvature of the fault. So that is very important, especially in a thrust fault and a normal fault. You can see that in a normal fault, then like this, the scarp is very short. But of course, there are some surface effect is also be considered. That's the only information I wanted to share. So this is what another scarp, what we see on the Mismi range of the Eastern Himalayan part, where we can see the fault scarp. So basically what this fault scarp basically tells, that we will discuss much later. Now, if you go to the transform fault, basically I'm showing most of the Indian examples. In this case, this is in Tangsei Valley in Leh region. You can see there is a stream offset. So wherever there is an offset, there is a disruption along this weak plane, we consider that a fault. It has a right lateral, left lateral movement. So based on that, we put the strike slip fault component with right lateral component with a left lateral component. So that leads to the different features like shutter ridge, all these things. It is not really required for you. Basically, it's all more detailed information, that which is not really required for you. So basically, I told you in the beginning that whenever there is a two stress or operating, we have the normal fault component. You can see that this blue arrow going down, but if you look at the fencing, it is more on a right laterally. So that means it has a both normal fault component as well as the strike slip fault component. So that kind of setup is always possible. It is not clear cut that it will have only this component. It will have a little bit of combination of both stress can be possible. That is what important. Now coming to the Himalayas. In Himalayas, we know that it is moving roughly at the rate of say 30 to 38 millimeter per year. So out of this 32 or 38 millimeters, the 20 millimeter is getting distributed just south of this Sangpo suture zone. I told you the suture zone is nothing but the meeting point or a welding point now of two continents. It is called, where we can see the beautiful classical example of ophiolitic melanges. That means that oceanic sediments are still preserved, which has come from a deeper level after the subduction that become an abduction process. So this 20 millimeter is getting distributed here. So basically we have a 38 millimeters and 20 millimeter is being consumed or accommodated within this Himalayan wedge. Then the rest of the 18 to 15 millimeter is getting accommodated in the Tibet regions, basically. So we are very much worried about this strain partitioning of 20 millimeter per year, because every year it is moving at this rate. So that means this convergence will lead to some repercussion. That's what we are getting, the micro earthquakes. So this can be seen very nicely in a cross section where the microseismicity and Himalayan seismic belts is all pointing that this Himalaya is growing and moving at a rate of this X and Y numbers, and it is moving vertically also. There are some SAR interferometry. There are many satellite products also suggesting there is a movement vertically as well as the horizontally. Now, if you look at these whole earthquake data, you can see very interesting observation is that if you remember my first slide, that is elevational differences. If I have that slide, okay, I can use this slide. This is the Brahmaputra plain and small baby mountain. Then we have the lesser Himalaya, we have the higher Himalaya. If I go back a little bit earlier, you see that there is the elevational differences from the plain to mountains. Now this is called the Himadri, or this green patch, where most of the pilgrim place or permanent snow peak mountains are available here. We say that it is higher Himalayas. Very interestingly to note that most of the microseismicity is totally confined on a topographic break where the foothills of the higher Himalaya. This is higher Himalaya, this is lesser Himalaya, this is sub-Himalaya. So make a point that most of the Himalayan seismic belt or seismicity lies on the foothills of the higher Himalayas. We don't have much seismicity on this foothills of the sub-Himalaya. We don't have seismicity on this, but seismicity is confining on the foothills of the higher Himalayas This is what these small dot shows. And even if the recent data set, the what I plotted, I'm sorry for moving the slide very fast, but there is no option. Okay, this is what I was trying to say that. So most of the Himalayan seismic belt is confined on the foothills of the higher Himalaya. Interestingly, what is happening there, the observation on a field or a geological observation is that there is a sudden elevational changes, number one. Number two, the Indian summer monsoon does not penetrate beyond this line. And this line is about 3,500 meter elevational difference. And this is the region where the Indian metacrustal ramp or Indian crust is underneath the Eurasian continent. So this is what most of the cross section we could infer from the deep seismic data set. We inferred this kind of geometry. This is what I was talking about, that southern part of the MCT or a foothills of the Himalayas. And if you look at the data set of the GPS also, you can see within these two gaps, you can see there is a velocity variation in the GPS. And another interesting aspect is that the northern part of this higher Himalaya is completely creeping in the sense that this is ductile. Basically, we know that the temperature gradient for the Earth's surfaces, every 1 kilometer, that is every 25 kilometers, that is a variation of the temperature gradients. That leads to this Indian lithospheres getting underthrusted. That gives the continuously creeping segment. That gives the asperity to create the earthquakes. Then most of the locking line, where these no microseismicity forms, that locking line is continuously storing the elastic accumulated strain that is being released in the form of earthquake time to time. So this is what I wanted to emphasize. Once these earthquakes occurs, depending upon the magnitude, it damages the earth surfaces. So I was talking about that this is the zone in which most of the static stress is getting released. When you go away from this region to region, that has become the most of the dynamic stresses. So we are mostly focusing on these areas that is called the foothills of the Himalayas, because in this case, the earthquake nucleation point is over here, but releases takes place on the foothills of the higher Himalaya, especially in a great earthquakes. This is what this cartoon says. Let's see some of the case studies in Himalayas. Basically, this is a big area where for more than 600 years ago, there was no earthquake happened between this Kangra region and to the Nepal region. This is very important. Basically, that's what it's the central seismic gap, because whole Indian government is also having worriness whether this area is when they will have a big earthquake on that particular regions. You can see that this is a simple, again, same cartoon, how this baby mountain to mature mountain forms. Basically, this is what this kind of observation we see on the field. So the question is that what is past is a prologue. That's basically that gives a lot of information. So now question comes that earthquakes do or do not follow any regular schedule. That is very important. So that's why we need to quantify how often this kind of an scar forms on the foothills of the higher Himalayas. So what we do, let's see what we do to know this question. So you can see this kind of a step-like features all along this Himalaya. That is a very common features in Himalayas. You can beautifully view that just like in a staircase geometry, one can walk across this mountain. So that is the beauty. Now, how to quantify this, basically? You know that this elastic strain accumulation is getting quantified using the GPS techniques, but the strain release, it cannot be quantified. So that means we need to understand the release pattern in the form of an geological records. That's what is important. So I'm going to talk on that part. That's how we use the trend study. Basically, primary paleoseismology or earthquake geology comes into the pictures. So what is the methodology we do? Basically, we use a lot of maps and the satellite imageries. That's for an just for a beginning of our research. We have to rely upon that because it's a very big area. So we have to narrow down some of the areas, then we use this. Then we use the topographic analysis. That's very important. So we use the total station and we use the R.J.G GPS, and also we use the sub-aerial survey using the drones. And we also use, once we understand the landform has been generated by earthquake. Now the question comes that when did this earthquake occur? That's the age. That means you have to date that landform, basically. That is very important. So that means dating technique is also very important. So we generally use the radiocarbon datings, and we also use the optical stimulated luminescence and the surface exposure dating. So I will be touching upon very little bit. This is what the GPS survey basically. Basically, we wanted to measure the orthometric or relative differences height. So we developed the local datum and try to collect the data set, and we developed the map for that. And we use also the drone, because every discipline, as I said earlier, they have a different purposes. Robotic sciences use the drones to study the control system, but as science, we fly a drone to observe the features because our eye base is very limited. So when you wanted to really map that entire area, you need to have a very good observations. So that's why we use the drone. So that's a small drone. What we use the quadcopter I bought from this Amazon, and we use the GoPro digital camera. Generally, they use for the stunt and other thing. And we fix it and we try to fly. And how do we do the georeferencing? Now the drone has come with the inbuilt GPS, and we don't have to do any kind of this kind of an ground control point, all these things. Now the technology has a little bit developed more, but still the ground control point is very important to relate the features which you take the photograph. That's a geotagging or georeferencing is very important. So that gives you more information. So what we do, that we use the typical survey tool, that is R.J.G GPS, and we flag with some paint, and we try to tag between the photo captured by the drone and this number. After all, it has a XYZ that will have a same coordination that gives the geotag figures. So this is how we fly the areas. So what is the use of that? Basically, you see there is an elevational difference of only 1 or 2 meters, but you can't really see on your eye, especially in a vegetated region. You can see that is the same elevational difference of 2 meters, basically. So this kind of information can be very well obtained from the drone technology. That's why we use this kind of a sub-aerial surveys. And this is another site. You can see the beautiful flat regions, and this is the flat region. There is elevational differences. The big scarp of 17th century, we took a big trench on this area in Arunachal Pradesh, and we dated this earthquake in 1697. There was a big earthquake, which is very well correlatable with the historical records. Okay, now comes to the age constraint. Basically, it is a matter of precision and accuracy. So we want both, basically. But at the same time, to obtain this, there are different dating techniques. As I said, that we use the calibrated radiocarbon. It has more or less having both precision and accuracy, even if the uncertainty may be in the order of 35 years or 40 years. But there are places the radiocarbon uncertainty is argued almost 500 years also. In those areas, the long-living species of trees, but in Himalayas, all short-living species. So we don't have such kind of uncertainty, but nevertheless, the uncertainty for prediction of whatever the, not prediction, or discovering of the older earthquake may be plus or minus 20 to 30 years. That's the uncertainty limit we have. So this is how we develop the radiocarbon samples. We collect the samples from the documented regions. And this is a cosmogenic sample. Basically, what is the meaning of this surface exposure dating? We are trying to understand how long this rock is sitting and seeing the atmosphere. Since when? That's the question, basically. Basically, this is the beryllium is getting generated with ablation processes. The silica is that oxygen is getting replaced with beryllium or aluminum automat, whatever the rock material depends. We try to see that processes and try to figure out that that's the surface exposure dating or a cosmogenic exposure dating. And this is the optical stimulated luminescence dating. Basically, these dating techniques is when was these sand grains seen the last sunlight? Because it got buried now. Now that particular, it is basically based on the principle of gap theory, basically, because this in the quartz grain on a lattice defects, some electrons get trapped and it will have some luminescent signal, and natural signal we regenerate in the lab, and we try to measure that dose and other thing that leads to the age for the optically stimulated luminescence. Okay, that's the dating part and mapping part is done. Now, what is this trend studies? Basically, the main question is that when, where, and its recurrence, as I said earlier. So main data set, we generally do a big hole on the foothills of the mountains, and also we try to collect the data set from the different destruction history from different city if there's been documented, and also whatever the map iso intensity maps, this kind of things we do. There are many methods like trenching, displaced geomorphic features, historical records. We use radiocarbon, as I said, cosmogenic luminescence datings. So what is the use of doing the trenching? So basically, we wanted to understand the faulting history. And once the faulting history is known, then how big the earthquake, how much movement has taken place along the particular fault. So that kind of information can be given. So this is how the trench looks. This is in the Sikkim Himalaya, where the big trench has been excavated. And this is a closer look. So we use such kind of information, and we do this almost 10-meter vertical offset, and we do the gridding, and we nicely document all this things and try to see, collect, and all the information. And this is another thing in Pasighat, how sometimes it gets collapsed because of the stability of the wall. There are many problems are there in things, and we try to use the total station to map this entire wall. That's how the trenching looks. So whatever the study we could do, we come up that there's a big model actually, what we have proposed based on this paleoseismology or earthquake geology, the nucleation of the earthquake on the interland part of the Himalayas. That comes all the way comes to the foothills of the sub-Himalaya. This is what a different theory or different model we are trying to develop for the different earthquake event with the different magnitudes. So basically, in the essence, this is what is happening. That's the mechanics of earthquakes in Himalaya. Basically, Indian plate is moving at the rate of 38 to 40 millimeters. So it is getting more and more energy is getting accumulated in the form of an elastic strain, and it leads to the some particular threshold limits. It emerges into a great earthquake or large earthquakes. That gives such kind of information. In nutshell, this is what this earthquake is happening in Himalayas. This, I think you can see many such kind of information from my book. So in a 3D perspective view, as I said, that this is the foothills of the higher Himalayas, where the locking line concept or a orographic barrier, all this observation, microseismicity lies on these foothills of higher Himalayas. So that means this is a locked segment, and it is continuously creeping segment. The potential energy is more, and this is continuously you are advocating the horizontal forces. So this whole block is accumulating the elastic strain release, and it will releases with different times. So that is the earthquakes. So why we study on this kind of an active fault? You see in Tenali Fault in America, they mapped a beautiful active fault, and there was a pipeline is crossing this active fault. So what this engineer did, they made this kind of an technology, because they know that this Tenali Fault is a right lateral fault. They also documented using this paleoseismology or earthquake geology, this fault can move maximum of 2 meter, 3 meter horizontally. So they got such kind of information based on the science, and they developed this technology. And this is what happened. So the Trans-Alaska pipeline was engineered to bend zigzag in response to movement on the Tenali Fault. The large arc in the pipe is due to shortening of the pipeline trace within the fault zone. Offset in the region was 8.5. So when we have such kind of informations, we can also utilize our science for safeguarding our infrastructures. But is there any such kind of attempt being made? This is not a criticism, but this is an observation. This is a railroad is being connected in the Riyasi and Katra regions. This is what the beautiful false scarp in Jammu. So no intervention of other discipline for resilient structures in Himalayas. So what is the bottom line? Great earthquake is really real. That means this irregular polygon of different colors is historically documented earthquakes. Some of them are discovered based on the paleoseismology, but most of the record from the historical documentation and paleoseismology is in harmony. But some places, not much information, but still more very rudimentary data set we developed. So in a central Himalayan seismic gap, almost 600 years past, 10 meters of slip is accumulated that you can imagine. So that means it is ready for an earthquake. I can't say it is great or large, but I do see the evidences on the foothills of the Himalayas. Hence, I am concluding it's a great earthquake. Of that means 8 magnitude. So this is what the population.
Dr. Perumal, sorry to interrupt. How
Yes,
many
sir.
minutes will you take more?
I'm done.
Okay. Sorry. Go ahead.
This is all. This is the population. Great earthquake is real. This is what the database we developed it. These are all the books. That's all. But there are many things. How the surface processes. It's all photographed. This is what the Kedarnath tragedy. The 12-meter block has saved the Kedar Mandir. So that's how it's being built on a previous history in the same fashion. Slowly, people will be considering. There are some factors which makes people believe. And these are all the big challenges in Himalayas, bank erosion. Why we ignore our ancient technology. Thank you. Thank you. I'm done.
Okay. Thank you, Dr. Perumal, for a very interesting talk. Now it is open for...
I think I have taken enough time.
No, also we started late. So certainly that's okay. So are there any questions? Let me see if there are any raised hands. Right now, I don't see any raised hands. But people, are there some participants in the hall in EG66?
Yeah, I've got a raised hand.
Yeah, then okay. Then please go ahead and ask.
Yeah. Dr. Perumal, I'm Sanjay Gokhale speaking.
Please, sir.
See, I just got 2 questions for you. I mean, they're not related to the discussion or the talk you've given, but then it's just a kind of information or knowledge I would like to gain from you. See, I'm talking of now the way the expansion of railways and tunneling is taking part in the northern part of our country. That is from Udhampur onwards till Baramulla.
Yes.
Railway line coming in. Like when we go to Manali, from Manali, the Rohtang tunnel has already been made. Likewise, when you go further up to Tangse and all, again, there also the tunneling has started taking place.
Yes.
How will all this affect in terms of, highlighted in terms of the things moving? That is point number 1 with the extreme north of our country. And one is to the extreme south of our country, that is the Andaman Nicobar Islands. Now there's a place called Kar Nicobar is an island in the Andaman Nicobar Islands. Fortunately, I served in that area. So there's a very unique thing when the tsunami took place. There was an overall tilt of about 4 degrees in the entire in the island. And we could see a distinct shift in the sea line, what it was, in 2003 and what it is now in 2022 or maybe 2005. We were told that the entire island is like an R-shaped glass, and the R shape which is there in the junction between the two, the upper and the lower part of the R-shaped glass might snap any minute. That is, what the knowledge is that, how do you relate that with geology is, in case you could tell us, it will be great. And there was one unique feature there on the island is a Japanese wells. Now, these were made by the Japanese in the Second World War for drawing fresh water for the troops when they were fighting the war, when the World War II was on. Now, the Indian Navy divers had gone inside, had seen everything there. They could not know the source of that sweet water which was generated in those wells, and they've been supplying sweet water for good about 75 years now overall. So these three things, in case in terms of geology and the way the plates move, in case you could just educate us, it will be great.
Yeah, see, I will take up one by one. Basically, the last, I will start with one from the beginning. You said that railway track is being getting expanded in northern margin of our country, but it's a good welcoming step. But at the same time, see, everything is getting tunneled. They use the tunnel boring machine. But the problem is that when before deploying the projects, they don't consider the geological discontinuity. Once they get a problem, then they consult the geologist. Like it happened in the Subansiri Lower River project. I did a big project on that for a seismic hazard assessment. When the initiation of the project, nobody bothered. But that's how it is basically in India. Basically, they presume that this is the particular threshold limit without studying the scientific or without generating the scientific data. The planner or administrator, they presume some numbers. You understand? So this is what it is. Then they start doing, because the engineering and technologists and scientists, basically this is the three people, they should go together. But it is, unfortunately, it is not happening. So for the first question, such kind of discontinuity, whether it has been taken into the consensus of the geosciences, I have no idea, but I did some collaboration work with what is that called, rights. They are, we gave one courses, but they generally use the some other consultant. I do not know much discussion on that, but in a similar instant in Parvati Valley, the NHPC is also facing a problem when they have a level 2 hydropower projects. So everywhere, whenever they get a problem, then the geologist being consulted. Number one. Number two, in the same aspects, this kind of a disaster or the fault which is going to develop a big damage to the infrastructure is not well mapped. In fact, our institute has done for the Uttarakhand regions, but it has not been done for the other part of the Himalayan states. Number two. Second question you asked that regarding the, what is that question? That is in Andaman Nicobar.
Andaman Nicobar, yes.
Andaman Nicobar. Okay, now basically what is happening, that there is a subduction is going on. So in the tsunami or any kind of an earthquake takes place, the land will go down. So during that processes, whatever the land mass having the perched aquifer or small aquifers, they go down. Once you identify these kind of places where the fault information is very clear, there is no surprise that you are getting a sweet water within the sea. Because after all, that particular continent, the block has gone down underneath the ocean. That is why the beauty of this paleoseismology is that you yourself realize you can't see, but it is covered with the sea. But in Himalaya, you can see on our naked eye. So that's why this paleoseismology science can be done in the Himalayas to develop a more and more scientific data set. Then we can have the resilient infrastructures that can be useful. So that is the same analogy I am just giving for you, because that particular land mass of used by the people has gone down after that particular earthquake or tsunami. From there, that's still that whatever the well is located, that you can't see.
Understood.
Makes sense?
Thank you. Thank you.
Okay.
Dr. Perumal,
Hello,
I had a question.
I have a question.
Oh, yes, please.
Okay. No. Okay. No, or let me ask it after Sukant. Sukant has raised his hand. So, Sukant, can you ask?
Yeah. My question is that how does the orogenesis of Himalayas differ from that of Western Ghats?
Yeah, that's very. Take 1 minute. Let me figure out how to video problem so that नहीं आ रहा ना? क्यों नहीं आ रहा वीडियो में? नहीं, उन्होंने बोला blank है.
Actually, there is some obstacle to that camera shutter is off.
Anyhow, but people may not see my face. No
Yeah,
problem.
that's okay. But please go ahead and answer the question.
Yeah, basically, sir, the Western Ghats and Eastern Ghats, they are the old orogeny landform, basically. Like they are our ancestors, basically. That's the answer for you. You see, they are relic mountains. They are relic mountains. But Himalaya is a young active mountains. So just imagine after 200 million years or 100 million years, we do not know the longevity of each of the orogen.
So
maybe
is it safe to assume that Western Ghats are they were formed actually during or even before Pangea formation?
no, not even Pangea. Don't go. That is Pangea as a whole. That's since from the beginning. But probably this is sometime in 550 million years ago. There is a Caledonian orogeny was there. There are many older orogeny has not been well studied, but still we say that Western Ghats and Eastern Ghats of different orogeny basically. But the timing of that particular orogeny is still we are doing the research on.
And
that.
how about Aravalis? And
Yeah, that is also Aravalli range and these Western Ghats, Eastern Ghats, they are much older than the Himalayan orogeny. So that's why there are combination of many orogenies. People, many geoscientists, they think that probably micro continent they propose, some of the people. So many micro continents, they were there and they all melded later on. But that's what, see, it's a very big research. Many people are working on piece and piece and how when this supercontinent really formed. So that's a big thing. But they are all older than Himalayan orogeny. So just imagine that they were Himalaya once upon their time. Now they are older now.
Okay, thank you.
Okay.
Okay, Alak, maybe you can ask your question.
Yes.
Yeah.
You showed a map towards the end where you were showing the dates of these earthquakes in the Himalayan region, and most of the timings were fairly recent, except for two in the Bhutan Sikkim regions. One was around 1100, another was 1200. Is it because as time progresses, it's more difficult to date these earthquakes, or is it that there are many such earthquakes and you just had labeled the most intense ones?
Yeah, see, whatever we are finding on the foothills of the sub-Himalaya is the intense one. Say magnitude minimum is probably 8. See, basically the magnitude is governed or decided by the total rupture length and width. This is what the equations. But the idea or the consensus is that since we are getting the geological signature on the foothills of the sub-Himalaya, with respect to the higher Himalaya, the horizontal distance is about 80 to 100 kilometer distance. So that's why we are bringing the magnitude, say 8. Number 2, when you talk about the age of the old earthquake, see, basically the earthquake which we had catalogued in a historically documented or instrumentally recorded documentations, there is a big gap whether this earthquake has really broken the surface, that earth surface or not. That itself not known. After the induction of this paleoseismology, we are confident that the particular earthquake has uplifted, say, 8 meters, 10 meters. So that's why we are very, very important for the historically known earthquakes. And we do have the older earthquakes. But if I go older earthquakes, people are not interested. Then when I go for older earthquakes, then they go for the repeatability of the earthquakes. See, I have a very small number of data sets. See, along the 2,500 kilometer Himalayan arc, the Wadia Institute, myself, that we have done about 30-35 trenches. So it's very insufficient to say or to confirm that by this is what it is. So that means we have the older earthquake also there, but we emphasize some of the earthquakes which has a historical documentations. And further that the earthquake has released most of the energy during that particular time. The question comes, we know that Himalaya is growing since its collision, say 50 million years ago. We do not know since 50 MA as on date, how much strain energy is being accumulated. We have no idea. We know that the instrumental documentation for the GPS is only started way back in 94. So that means we presume a steady state of model from 94 to 2022, in the India-Eurasia convergence that gives the accumulation at the rate of some particular meters. Then out of that, this much earthquake has been released. Basically, it is a slip deficit. We are all making an hypothesis that only for a limited times, but it does not do with the, but one more important information, you rightly said that if the larger the time, if the small landform has developed, for example, 1950 has produced a 10 meter of elevational difference. After 50 years or 100 years, you may not be able to see the evidence for the 1950 earthquake because the surface processes, because it's a monsoonal terrain, it can erode. So that means there is a most likely chances for preservation potential of that particular landform is related to the cumulative effect of many earthquakes. Because this is a big challenging. You rightly pointed out that the longevity of the scarp, then people started working how far the 8-meter scarp can withstand in a monsoonal terrain. You understand? That's why the geology subject is very complex. But you have to study each and every intricacy of the particular problem, you will succeed it. I think it makes sense what I give a reply.
Yes, it does. I had just one other question related. This 1100 AD and 1200, you had historical records. What kind of historical records were there?
Yes. Yeah, see, that's a good point. In Nepal, I forgot this king name. I'm sorry, because it confused with Vijay Malaya name. So there was a documentation in Nepal historical archives. There was an earthquake in 1255. And there was a documentation of 1344. That is also documented. Even in Iyengar from IISc Bangalore, he has very well compiled all the historical documents. So these are all some of the earthquakes. But now the 1100 AD basically is a mismatch. Basically, many of the American scientists, they argue there was an earthquakes. That's what I'm seeing now. As such, 1100 AD does not exist in catalog. 1255 and 1344 is existing. Now, since it was, hypothesis was proposed by some American, but people still lingering around the 1100 AD. But I don't think so. That is a 1100 AD earthquake, since it has not been documented. But it is also possible that probably historian is forgot to mention that particular earthquakes. But that's what I have answered for you.
Thank you.
Dr. Perumal, I had a question
Yes, please.
on this Tehri Dam. What do you think is the risk involved for Tehri Dam? Because this was a discussion quite some, a few years ago, and
yes.
discussion that.
Yes. I think in your time, Professor Khatri, now he's passed away. See, I don't think so. There is any risk actually. Okay. In fact, what are you doing when you are constructing a dam? Let us think in a scientific manner. You are adding some potential energy more, isn't it? Yeah. So that means that whatever the horizontal forces will be minimized. In a way, if you think in that aspect, see, the release of energy, the devastation is something different. I am talking about the deployment or embarkment of the dam does not increase the seismicity. This is what my answer is.
Okay, so no, I think there was also this discussion on what would happen if an earthquake occurs. Will that structure withstand that? So of course, the civil engineers have some answer to that. They say
no, that's what I told you.
But what is the chance of a big one hitting there?
That's what Professor Vivek, I told you at the beginning.
Yeah.
See, the civil engineer, planner, technologist, or even a scientist, other scientists, what they say that, see, we have a technology. It is also true. Taiwan is growing at the rate of 80 millimeter per year. They have a biggest Taipei tower. So the traffic is there. You have to walk on the road. So I'm not making people scary. That is a technology. But they should also equally take the consensus, the data set, but they presume the ground acceleration due to earthquake, the vibration or whatever you say, that acceleration due to gravity of 8 magnitude, they always keep in consideration. If it is going beyond 8, that means they keep the G value of 1. If it is going more than 1, it's a total devastation. Then just forget about the things. You understand my point?
Yeah.
See, they make a one limit. So that's why they don't take our data set inside to the consideration, because they are doing a pigeon hole research. Their mind is biased. They fixed a 1G. Why should they work about G? Say G kya lena dena? You understand that? Na?
Okay.
Whatever the scientific record you develop, it is a bread and butter for us. But actual integration, amalgamation, melding of science, technology, engineering, planner, administrator is not happening. That's why in our country, most of the decision is made by the planner. I'm sorry. I'm not frustrated. You see the IAS, he says, I'm only doing the big work for the nation. But myself, even Chaprasi also contributing. Even auto rickshaw fellow is contributing because he is taking me to some other place. So every human being is contributing. But when everybody started realizing each and everybody's contributions, then there will be a spiritual. So science and spiritual, that's how it happens. So if you ask me, this is what the answer is. But in a technical manner, they already presume some number.
Okay.
Can I ask a related question?
Okay. Maybe
yes.
that's the last question because we are already 25 minutes ago.
Yeah. So I mean, when you build a dam, you also have a reservoir around it, and that's a fairly large amount of mass of water. Does that in any way contribute to the instability, the possible instability in that region, or is that really too small?
Okay, Dr. Ray, I want to ask you one question to you. It is anthropogenic. That's why you have a concern, isn't it? Because it was made by the civil engineer or maybe a planner or administrator. Now the big Himalaya is there. What is their impact on that? Now just think about it. Okay, just for a food for your thought. Now, when you have the reservoir-induced seismicity, it will not affect much of the regions. It will have maybe magnitude of 2, 3. That is very, very small. So we can't say, see, we need to have the technology development. So we can't scare the people that reservoir can, but even see Koyna Dam. What is the magnitude? There's only one earthquake has produced, that Koyna Dam reservoir-induced seismicity. So there is a likelihood for developing a reservoir-induced seismicity. Now, whether they can surpass the Himalayan seismicity, that's a big question. I think you got my answer, or still it is in kind of?
Yeah, kind of. Yeah.
Okay, because that's the answer is only kind of only.
Okay. Thank you. Thank you very much.
Thank you, Ray.
Okay, so are there any questions, Shinde, on YouTube? Then you can read them out.
No, sir. No, sir.
Okay. Then I think let's draw this to a close. Let me thank Professor Perumal for this very invigorating lecture, and thank you very much. And we'll close.
Thank you, Professor Vivek, and
Yes.
thank you to all of you, and thank you to Tata Institute of Fundamental Research. Have a good evening, and thank you very much. Bye.
Thank you.
Thank you, sir. Thank you, sir.
Thank you. Thank you. Thank you, Vivek.